Bismillahirrahmanirrahim. My dear students, Assalamu alaikum. I am going to teach you the course of Basic Electrical Engineering. This is your second semester. And different books are recommended for this particular course. You guys can study the Basic Electrical Engineering by Fitzgerald. I recommend the 5th edition of this particular book for my course. Then Electrical Technology by B.L.T. Raja and Electrical Technology by Edward Hughes. I recommend you my personal book which I published back in 2019. The language of my personal book is very simple. You guys can learn the derivation of simple equations and some solved simple numerical examples that helps you to understand the course of Basic Electrical Engineering. Let us start chapter number 1. In chapter number 1, I am going to define electrical energy and voltage. After this lecture, you guys will be able to know the electrical energy, like what is electrical energy, what is the mathematical equation that is used to find out the electrical energy of an electrical system. What is the potential difference or voltage between 2 points? How do we calculate the potential difference or voltage between 2 points? Voltage is electrical energy as well, and if you guys want to have a current in a conductor or in a circuit, you guys need to apply some energy which is known as voltage across the circuit. And then we shall talk about the Ohm's law. Okay, what is Ohm's law? And then we will talk about a capacitor. We shall consider the construction of a capacitor, the equation which is used to find out the capacity or the capacitance of a capacitor. How do we calculate the voltage across a capacitor? How do we calculate the current through a capacitor? How do we calculate the power supplied by the source to the capacitor? And how do we calculate the energy which is stored in the electric field of the capacitor? And blah, blah, blah. So let us start to see the electrical energy. Well, in this very course, we are dealing with two different types of quantities. The electrical quantity which is constant with respect to time, the magnitude of which is constant with respect to time, is represented by a small letter in this particular course. You see Q in this particular topic is represented by capital Q. It will be represented by capital letter. The time constant electrical quantities will be represented by capital letters. So you see here we represent the charge by capital Q. It means that this charge is not, the magnitude of this charge is not changing with respect to time. If it is changing with respect to time, we will represent it by small q. Similarly, the energy is the electrical energy is represented by W. If it is capital W, it means that the magnitude of this energy is not varying with time. If it is changing with respect to time, we will represent it with the help of small w. and so on. If we have the electrical power, we know that the electrical power is represented by P. So the constant power will be represented by capital P, and the time varying power will be represented by small p. So all the time varying quantities will be represented by small letters, and all the the time constant electrical quantities in this course will be represented by capital letters. What is electrical energy? So let us consider an electric field in this particular region. There is an electric field in this particular region. We know that the electric field intensity is a vector quantity, and this quantity has a magnitude as well as direction. And you guys know the definition of electric field intensity. We know that electric field intensity is a force, and force is a vector quantity. So if electric field intensity is a force, and as force is a vector quantity, then definitely electric field intensity is a vector quantity as well. This is the force on a unit positive charge. The force per unit positive charge is known as electric field intensity, and as I have already mentioned, that electric field intensity is a vector quantity. So as far as this arrow is concerned, this arrow represents the direction of the electric field intensity in this particular region. We consider 2 points in this electric field. One point is represented by A, and the other point is represented by B. So we consider 2 points. In the given electrical field. And what we want to do, we want to move a charge of q coulomb from the initial position B to the final position A against the field. Definitely some energy will be required to move this charge of q coulomb from the initial position B to the final position A against this electric field. So the amount of energy which is required to move a charge of q coulomb from the initial position B to the final position A against the electric field is known as electrical energy. And electrical energy is represented by W. So electrical energy is represented by W, and time varying electrical energy is represented by small w. The unit of energy is watt seconds. So if we want to calculate the electrical energy which is required to move this charge of q coulomb from the initial position B to the final position A against the electrical field, we need to know the distance between these 2 points. So we need to know the distance between these 2 points, and let's say the distance between these 2 points is represented by D. And we apply a force on this charge of q coulomb to move it from the initial position B to the final position A. Some work will be done in this particular force. Some energy will be expended in this particular course. So the work done in this particular case will be equal to the product of the force and distance. So the product of the force and distance will give you the electrical energy, which is which is required to move this charge of q coulomb from the initial position B to the final position A against the field. Well, we know that electric field intensity is a vector quantity. So electric field intensity is a vector quantity, and electric field intensity is the force per unit positive charge. So the force per unit positive charge is known as electric field intensity, and definitely the force in this particular case will be equal to the charge multiplied by the electric field intensity. This much force will be required to move this charge of q coulomb from the initial position B to the final position A against the field. So we put the value of this force in equation number 1.1. So if we put the value of this force in equation number 1.1, we obtain equation number 1.2, and equation number 1.2 gives you the electrical energy which is required to move this charge of q coulomb from the initial position B to the final position A against the electric field. This is how we calculate the electrical energy. So if we know the charge, the magnitude of the charge, and if we know the electric field intensity in the given region, and if we know the distance between the 2 points, so we can calculate the electrical energy with the help of equation number 1.2. This is one way to calculate the electrical energy. I am going to derive another equation for the electrical energy in a while. Well, let us talk about the voltage or the potential difference between 2 points. So we consider an electrical field in this particular region. The electric field intensity is a vector quantity. This vector quantity has a magnitude as well as direction. So as far as the direction of the electric field intensity in this region is concerned, the direction of the electric field intensity is given by this arrow. We want to find out the voltage or the potential difference between these 2 points, and these 2 points are located inside the field. So voltage is an electrical energy. Please keep it in your mind that voltage is electrical energy. And this electrical energy moves a charge from one point to another point, which is known as current. We know that the rate of the motion of charge is known as current. So voltage is an electrical energy, and this electrical energy moves a charge from one place to another place, and the motion of the charge in a conductor is known as current. So we consider 2 points A and B in the given field, and we want to find out the potential difference or the voltage between these 2 points. So in order to calculate the potential difference or the voltage between these 2 points, we move a unit positive charge. That is a charge of 1 coulomb. So we move a unit positive charge from the initial position B to the final position A against the field. So if you guys want to move a unit positive charge from the initial position B to the final position A against the electric field intensity, definitely some energy will be required. And the amount of energy which is required to move a unit positive charge from the initial position B to the final position A against the given field is known as potential difference or voltage between these 2 points. So, the amount of energy which is required to move a unit positive charge from one point to another point against the field is known as potential difference. You see, we know that this much energy is required to move a charge of q coulomb from the initial position B to the final position A. The magnitude of the charge in case of equation number 1.2 is q coulomb. If I want to find out, you see, this if I want to find out the potential difference between point A and B, I need to replace this charge of q coulomb in equation number 1.2 by 1 coulomb. So if we replace this charge of q coulomb in equation number 1.2 by 1, you guys will be able to find out the voltage between point A and B or the potential difference between point A and B. So the voltage between point A and B will be equal to the energy which is required to move a unit positive charge from the initial position B to the final position A against the electric field intensity. This much energy will be required, and this energy is known as voltage now. And you guys can find out, you see, the voltage if the total electrical energy is known, and so the total electrical energy divided by the total magnitude of the charge will give you the voltage between these 2 points. Or if you know the electric field intensity in this region and the separation between these 2 points, you guys can find out the voltage with the help of the electric field intensity as well as the separation between these 2 points. So the voltage between points A and B is given by equation number 1.3. So the total electrical energy divided by the magnitude of the charge will give you the voltage between these 2 points. And if you divide both sides of equation number 1.2 by the magnitude of the charge, we obtain equation number 1.4. So we can calculate voltage with the help of equation number 1.4 as well. If we know the electric field intensity in this particular region, and if we know the distance between these 2 points, we can calculate the voltage between these 2 points. So voltage is electrical energy. This electrical energy moves charge from one place to another place. And the rate of motion of charge in a conductor defines current. So the rate of motion of charge is known as current. If the current is constant with respect to time, we shall represent this current by capital I. So the constant current in this course will be represented by capital I. The DC current in this course will be represented by capital I. If the magnitude of the current is changing with respect to time, then this current will be a time varying current. This current will be represented by small I. So the time varying currents in this particular course will be represented by small I. The AC current, we know that the magnitude of the AC current varies with time. So the AC current will be represented by small I as well. So equation number 1.5 gives you the current in a conductor. The rate of motion of charge is known as current. Now let us define electrical power. Electrical power is represented by P. If the electrical power is constant with respect to time, it will be represented by capital P. If it is changing with respect to time, if the magnitude of this power is varying with time, then it will be represented by small p. And what is electrical power? The electrical energy per unit time is known as electrical power. And the unit of the power is watt. So the energy per unit time is known as electrical power, and electrical power is measured in watts. So the total electrical energy divided by the time will give you the electrical power. We know that the voltage between these 2 points, or between any 2 points, will be equal to the total electrical energy divided by the magnitude of the charge. So you guys can calculate the total electrical energy in terms of voltage and charge. So the total electrical energy in terms of voltage and charge will be equal to QV. So we put the value of electrical energy in equation number 1.6. The electrical energy is equal to QV. So the electrical power will be equal to QV by T. This is how we calculate the electrical power. And as I have already mentioned, that the unit of the electrical power is watt. Well, the unit of the electrical energy is watt second. Let me clarify one thing over here. You see, we use electrical energy in our houses, schools, markets, universities, classrooms, blah, 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 right? So we consume electrical energy. And we say that I have consumed 200 units of electrical energy. Now the unit which is used in our houses is kilowatt hour. It is not watt second. So 1 unit is 1 kilowatt hour. I'm talking about the unit in our houses. We pay to the utility center in terms of units. So if I have consumed 200 units, it means that I have consumed 200 kilowatt hour. It means that I have consumed 200 kilowatt per hour. Anyhow, let us come back to equation number 1.7. We know that the rate of motion of charge is known as current. So, if we put the value of the current in equation number 1.7, the electrical power can be calculated with the help of this equation. So the product of the voltage and current gives you what? It gives you electrical power. So we can calculate the power with the help of VI. And if you look at equation number 1.6, equation number 1.6 gives you electrical energy, and electrical energy will be equal to PT, watt seconds. And what is P over here? P is the product of the voltage and current. So we can calculate the electrical energy with the help of this particular equation as well. VIT, the product of the voltage, current and time, will give you electrical energy. This is another equation which is used to find out the electrical energy. Let us do equation number 1.1. I have designed this numerical example in my personal book for you guys. I advise you guys to buy the book. It will help you a lot. The price of my personal book is rupees 1000, and let me make it clear that it is on the basis of no profit and no loss. It is on the basis of no profit and no loss. So this is example number 1.1, which is from my personal book. So example number 1.1 states that a 12-volt battery is charged for 4 hours with a current of 2 ampere. 60% of the energy is stored as chemical energy, and the remaining energy is lost. So we shall calculate the total electrical energy. Out of the total electrical energy, 60% of the energy will be stored in the battery as a chemical energy, and 40% of the energy of the total energy will be lost. If electricity cost rupees 0.02 per watt second, then determine the cost of charging the battery. The amount of energy that is stored as a chemical energy and the energy that is lost. So in this numerical example, we need to calculate 3 different quantities. We need to calculate the energy which is stored as a chemical energy in the battery, the energy which is lost during this charging process, and the cost of charging the battery. So we will have to calculate the total electrical energy in watt seconds. We know the price of 1 watt second. We can calculate, you see, the cost of the total electrical energy with the help of this unit. Then 60% of the total electrical energy is stored in the battery as a chemical energy. We will calculate 60% of the total electrical energy, which will be the amount of energy which is stored in the battery as a chemical energy. And definitely 40% of the electrical energy will be lost. Okay? So let us do this numerical example. Now, how much voltage do we need in this particular case? We need to charge this battery with the help of a system, with the help of a charger, which will have 12 volt. And the current which is needed to charge this battery is 2 ampere. So the voltage in this particular case is 12 volt, and the current in this particular case is 2 hours. We fully charge this battery in 4 hours. So let us convert this time into seconds. So we multiply this 4 by 3600 and we get 14,400 seconds. So the battery will be charged fully in 14,400 seconds. Let us calculate the total electrical energy in this particular case, and we know that the total electrical energy will be equal to the product of the voltage, current, and time. Okay, so the product of the voltage, current, and time will give you electrical energy. So we calculate the electrical power with the help of this equation. The product of voltage and current will give you the electrical power, which is 24 watts. And then we calculate the energy with the help of this particular equation. The product of the electrical power and time results in energy. So the total electrical energy is 3,45,600 watt seconds. We know the cost of watt second, which is 0.02. So 1 watt second costs 0.02. Definitely 3,45,600 will cost rupees 6,912. So this will be the cost of charging the battery. Now 60% of the energy is stored as a chemical energy. So the total energy multiplied by 60% will give you this much joules. So this much energy is stored in the battery, which is 2,07,360 joules. The remaining energy is lost. So this is the total electrical energy. This much energy is stored in the battery as a chemical energy. Definitely the total electrical energy minus the energy which is stored in the battery as a chemical energy will give you the energy which is lost. So this much energy is lost in this particular process. Okay, let us talk about resistor and Ohm's law. Resistor is a passive circuit element. What is a passive circuit? What is a passive circuit element? So any circuit element which takes energy from the voltage source is known as passive circuit element. Resistor takes energy from the voltage source. We call it passive circuit element. Similarly, inductor takes energy from the voltage source. This is an example of the passive circuit element as well. Capacitor takes energy from the voltage source. So capacitor is an example of passive circuit element as well. So the circuit elements which take energy from the voltage source are known as passive circuit elements. And the circuit elements which deliver energy to these passive circuit elements are known as active circuit element. So voltage source is an active circuit element. Similarly, current source is an active circuit element. So we consider a very simple diagram over here. We apply some voltage across this resistor. Resistor is a passive circuit element. Whenever we apply voltage across a passive circuit element, it results in a current in the passive circuit element. Whenever we apply some voltage across a passive circuit element, it results in a current in the passive circuit element. The voltage across the source is a time varying voltage. This is why we represent this voltage with the help of small v. Usually, the nature of the current depends upon the nature of the applied voltage. Usually, the nature of the current in a circuit depends upon the nature of the applied voltage. What do I want to convey to you guys? You know what do I mean? I want to say that if the voltage is constant with respect to time, then the current in this simple circuit will be constant with respect to time. And if the magnitude of the voltage is changing with respect to time, then the magnitude of the current will be varying with respect to time. So as there is a time varying voltage across the resistor, there will be a time varying current in this particular circuit, and this time varying current is represented by small I. All the time electrical quantities in this course will be represented by small letters. Well, there are two types of voltage sources. Let us consider a voltage source. There are two terminals of the voltage source, negative and positive. So if the current flows from a negative terminal, from the negative terminal of the source towards the positive terminal, the voltage of this voltage source will be known as voltage rise. Let me write it down for you guys. The voltage of this source will be known as voltage rise. So whenever the current flows from the negative terminal of the voltage source towards the positive terminal, the voltage of the source will be known as voltage rise. And if the current flows from the positive terminal of the source towards the negative terminal, then this voltage of the source will be known as voltage drop. So I consider the current in this direction. You see over here the current flows from the positive terminal of the source towards the negative terminal of the source. So this voltage will be known as a voltage drop. So if the current flows from the positive terminal of the voltage source towards the negative terminal, the voltage will be known as voltage drop. Let me repeat. If the current flows from the negative terminal of the voltage source towards the positive terminal, the voltage of the voltage source will be known as a voltage rise. And if the current flows from the positive terminal of the source towards the negative terminal, as the case is over here, the voltage of the source will be known as a voltage drop. You know what is a voltage rise? and voltage drop. So let us come back to this simple circuit. We apply a time varying voltage across the passive circuit element. There are two different types of circuit elements in this simple circuit. One is the voltage source, which is known as active circuit element because it delivers energy. And the other one is a resistor, which is known as passive circuit element. Why? Because resistor takes the energy from the voltage source, so it is passive. Whenever we apply some voltage across a passive circuit element, the voltage results in a current in the passive circuit element. And the nature of the current usually depends upon the nature of the applied voltage. If the voltage is constant with respect to time, then current in this circuit will be constant with respect to time. And if the voltage is varying with time, then the resulting current will be varying with respect to time. Whenever there is a current in a passive circuit element, the current in a passive circuit element results in a voltage drop. You see, the current flows in this direction in the resistor. The plus polarity of the voltage source is on this side and the minus polarity of the voltage is on this side. So the current flows from the plus polarity of VR towards the minus polarity, and this is a voltage drop. So whenever there is a current in a passive circuit element, the current results in a voltage drop across the passive circuit element. So the current results in a voltage drop across the passive circuit element, which is VR, because the current in this resistor flows from the plus polarity of this voltage towards the minus polarity. So this voltage is known as voltage drop. Let us consider the direction of the current in the voltage source. The current inside the voltage source flows from the negative terminal of the source towards the positive terminal. So this is a voltage rise. And this is a voltage drop. We apply KVL to this particular loop. We apply KVL to this particular loop. You see, the current flows in the clockwise direction in this loop. And KVL states, let us go towards KVL. And KVL states that the sum of the voltage rises in this loop will be equal to the sum of the voltage drops in this particular loop. This is the statement of KVL. The sum of the voltage rises in this loop will be equal to the sum of the voltage drops. You see, keeping in view the direction of the current, as the current flows from the negative terminal of the source towards the positive terminal, so the voltage across the source is a voltage rise. And the same current flows from the positive terminal of this voltage towards the negative terminal. So the voltage across the resistor is a voltage drop. So according to KVL, the only voltage rise in this loop will be equal to the only voltage drop. So Vs in this particular case will be equal to VR. This is in accordance with KVL. KVL states that the sum of voltage rises in a loop is equal to sum of the voltage drops. So there is only one voltage rise in this loop, which is voltage across the source, that is Vs, and only one voltage drop in this loop, which is Vr, and which is the voltage across the resistor. So Vs is equal to Vr in this particular case. What is Ohm's law? Ohm's law states that the voltage across a resistor is directly proportional to the current in the resistor, provided the resistance of this resistor is held constant. The voltage across the resistor is directly proportional to the current in the resistor, if the resistance of the resistor is constant. If we increase the current in the resistor, the voltage across the resistor, I am talking about Vr as well as Vs. So the voltage across the resistor will increase. And if we decrease the current in the resistor, the voltage across the resistor will decrease. In other words, the current in the resistor is directly proportional to the applied voltage if the resistor is constant. By increasing the voltage across the resistor, the current increases, and vice versa. By decreasing the voltage across the resistor, the current in the resistor will decrease. So definitely VR will be equal to IR. This is how we calculate the voltage across this resistor. And if you want to calculate the current in the resistor, the current in the resistor will be equal to VR by R, the voltage across the resistor by the resistance of the resistor will give you current in this resistor. So you know how to calculate the voltage across the resistor if the current is known, and you know how to calculate the current in the resistor if voltage across the resistor is known. Well, we transmit electrical energy from Torbella powerhouse to Peshawar. There is a powerhouse in Torbella, and our university is situated in Peshawar, is located in Peshawar. So the electrical energy is transmitted from Torbella powerhouse to Peshawar with the help of conductors, with the help of transmission lines which are made of conductors. And conductors have a resistance as well. What is resistance? The opposition which is offered by an element to the flow of current. The opposition which is offered by the conductor to the flow of current is known as resistance of the conductor. So the resistance of a conductor depends upon three parameters in equation number 10. It depends upon the material of the conductor, which is known as resistivity, the nature of the material of the conductor. Silver has got different resistivity, gold has got different resistivity, copper has got different resistivity, aluminum has got different resistivity, and so on. And this resistance is directly proportional to the length of the conductor as well. If you increase the length of the conductor, the resistance of the conductor will increase. And the resistance is inversely proportional to the cross-sectional area of the conductor. By increasing the cross-sectional area of the conductor, its resistance decreases. So anyhow, if you guys want to transmit electrical energy from one station to another station with the help of transmission lines, these conductors or transmission lines will have some resistance, and definitely these resistance will offer opposition to the flow of current. Some energy will be lost in the resistance of the conductors as well. Anyhow, the voltage across the resistor is directly proportional to the current if the resistance of the resistor is held constant. What I do, I consider the graphical presentation of Ohm's law over here. Figure number 1.4 gives you the graphical representation of Ohm's law. We take the voltage across the resistor along horizontal axis and the current along the vertical axis. So if we increase the voltage across the resistor, the current in the resistor will increase. This is the graphical representation of Ohm's law. We get a straight line which is passing through the coordinates of this graph, which is passing through the origin of the two coordinates. So this kind of relationship is known as linear relationship. If we get a straight line between the voltage and current like this kind of relationship is known as linear relationship. And any circuit element which has a linear relationship between the voltage and current is known as linear circuit element. Any circuit element which has a linear relationship between the voltage and current is known as linear circuit element. So this is the relationship between the voltage and current of a resistor. It means that resistor is a linear relationship. In other words, as resistor obeys Ohm's law, so this is why resistor is known as linear circuit elements. अफजल खान साहब सॉरी पर क्लास के रिकॉर्डिंग को मस्तान आवाज पके राजी लग सबरो की खा Okay, I'm sorry for receiving the call of Dr. Professor Afzal Khan from the Department of Mechanical Engineering. I forgot to take my mobile phone to the flight mode, so I'm sorry for the disturbance, okay? So any circuit element which has a linear relationship between the voltage and current is known as linear circuit element. In other words, any circuit element which obeys Ohm's law is known as linear circuit element. Resistor is a linear circuit element because if you increase the voltage across the resistor, the current in the resistor will increase linearly and you guys will get a straight line between these two quantities. Inductor is a linear circuit element as well. If we increase voltage across the resistor, if we increase voltage across the inductor, the current in the inductor will increase linearly. In that particular case, the inductive reactance of the inductor is constant. We will talk about, these quantities later on. So there is a linear relationship between the voltage and current of an inductor as well. Inductor is a linear circuit element. Similarly, if you guys consider the example of a capacitor, it is a linear circuit element as well. If you increase the voltage across the capacitor, the current in the capacitor will increase linearly. So there are three linear circuit elements: inductor, capacitor, and resistor in the course of basic electrical engineering. If you consider the example of a diode, diode is a non-linear circuit element. Why? Because the relationship between the voltage and current in case of a diode is non-linear. So it's a non-linear device. I'm talking about diode. Anyhow, we consider this simple circuit once again. There are two circuit elements in this simple series circuit. One is the passive circuit element, that is resistor, which takes the energy from the voltage source. And the other one is the voltage source, which delivers energy, which delivers power to the resistor. And there is a law which is known as the law of conservation of energy. And you know the law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed. It can be converted from one form to another form. So the power which is supplied by the voltage source according to the law of conservation of energy will be equal to the power that is taken by the resistor. So the power supplied by the voltage source will be equal to voltage across the source multiplied by the current. The product of these two quantities will give you the power which is supplied by the voltage source. And the power taken by the resistor will be equal to VRI, the voltage across the resistor, and the current in the resistor. This is one way to calculate the power consumed by the resistor. This resistor will consume power. This energy will be converted into heat energy, and if this is not the resistor of the heater, definitely this energy will be lost in the atmosphere as a heat energy. We know that VR is equal to IR. If I put the value of VR in this particular equation, I obtain another equation for the power which is consumed by the resistor, that is equal to I square R. So we can calculate I with the help of this particular equation as well. You see, we have the current which is basically equal to VR by R. If I put this value of the current in equation number 12, I get another equation for the calculation of the power, which is VR square by R. So we can calculate the power with the help of any one of these three equations. Let us do a very simple example. This is example number 1.2 from my personal book. Let the voltage across the source in the circuit diagram of figure number 1.3 is 10 volt. And resistance of the resistor is 5 ohm. Determine the current in the resistor and power consumed by it. So we know that the current will be equal to voltage across the resistor by the resistance of the resistor. Voltage across the resistor is 10 and current in the resistance of the resistor is 5. So current in the resistor will be 2 ampere. We know that the power supplied by the voltage source will be equal to the power consumed by the resistor, and we can calculate the power consumed by the resistor with the help of this particular equation, that is I square R. So we have 4 into 5 and we obtain 20 watts. So the resistor of figure number 1.3 will consume 20 watt. Thank you so much We will talk about another passive circuit element in the upcoming class, which is capacitor, and then another passive circuit element in the upcoming class, which is inductor. Thank you so much so far. Okay.